The feedstocks used for the manufacture of cement are the natural raw materials limestone and clay. These are broken down in crushers into fragments of about 1 kilogram and then ground in a raw mill, together with smaller amounts of iron ore and quartz sand to obtain a fine meal. At the same time, they are dried with the hot kiln exhaust gases from the incineration process. This raw mix is then transferred to a rotary kiln and fired at temperatures of about 1450 degrees Celsius to produce round-like particles measuring about 3 centimeters, known as cement clinker. Sintering is the name used by experts to describe this important process, which needs an enormous amount of energy. In this incineration process, chemical compounds are formed which later cause the cement to harden when mixed with water. After the incineration process, the cement clinker drops out of the kiln and is cooled to about 200 degrees Celsius in a grate cooler. After adding gypsum or anhydrite and sometimes further ground additives like slag, fly ash and limestone, the clinker is ground in mills to produce fine cement. The quantity and type of the additives influence the chemical and physical properties of the cement. The cement is stored in silos and is mostly supplied to concrete manufacturers as bulk material for further processing. Concrete consists mainly of a mixture of cement, water and aggregates such as sand, gravel and crushed rocks. At the concrete manufacturing plant, the cement powder from the storage silo is transferred to the mixer. All the concrete components are weighed exactly before being added to the concrete mixer for a specified time. Finally, the chemical admixtures like the superplasticizer glenium is added. In this process, the cement-water admixture slurry becomes the glue, also known as cement paste, that holds the aggregates together. The fresh concrete mass then flows into mixer vehicles to be transported to the construction site. The properties of concrete can be specifically varied by using different mixture proportions and admixtures. The admixture glenium, for example, increases the flowability of the concrete so that the densely packed steel reinforcement bars of a foundation can be coated quickly and completely with concrete within a short time. A pilot plant comparative study between conventional concrete and concrete with added glenium, but with the same water content and mixing ratio, clearly shows. With conventional concrete, the flow process already stops after 5 seconds and after a distance of about 25 centimeters. Concrete to which the superplasticizer glenium was added flows much faster, and the distance traveled over the same period is about 65 centimeters. Modern superplasticizers like glenium are based on synthetic organic polymers such as polycarboxylate ether, called PCE for short. A PCE molecule consists of one long main chain and shorter side chains. The main chains are negatively charged. When cement is mixed with water, it reacts and starts to form crystalline needles that interlock with each other to form a hard, rock-like substance. When the PCE molecules are mixed with liquid concrete, they are absorbed onto the surfaces of the particles contained in the concrete. The side chains of the molecules point outwards, like the spines of a chestnut burr, and hold the particles at a distance to each other. This makes it easier for them to move against each other, and the concrete becomes more fluid. Concrete can be given the desired properties by varying the length of the main and side chains.
You could say that interlocking concrete pavers came out of the rubble of World War II. In post-war Holland, there weren't enough clay pavers to rebuild city streets, so the Dutch began making concrete pavers. The Germans refined the technology and exported it to North America, where they found a quick road to success. Call it a concrete solution for paving. These pavers are solid, and the interlocking design disperses weight, easing the load on the road. To make these pavers, a conveyor belt delivers concrete sand to a weigh belt that weighs the coarse sand as it falls onto it. The weigh belt carries the sand forward. while another conveyor belt unloads stone chips to be weighed. These chips are no larger than 1/3 of a centimeter. The ratio of sand to stone chips varies depending on the type of paver being made. The weigh belt transports the stone chips forward along with the coarse sand. Both are en route to the skip hoist. They spill off the conveyor into the skip hoist, which is essentially a bucket on rails. Cables pull the loaded bucket upwards. It stops about 9 meters up, just above a big concrete mixer. A trapdoor opens and dumps the sand and stone chips into the mixer. 6 giant steel paddles mix and then rotate and mix again, while cement is added automatically through several nozzles on the side of this enormous mixing bowl. Making pavers is a bit like baking cookies. Too much or too little liquid in the batter and it won't bake properly. Water is added until the consistency is just right. Nozzles also shoot a pigment into the mix to tint it. The mixture looks dry and crumbly, but the recipe gives it just enough moisture to form the concrete. Now a filling wagon spreads the mix over a steel mold containing up to 50 paver-shaped cavities. The mold press head applies 10 tons of vibrating pressure. This pulsating force compacts the mixture into the paver mold and removes any air pockets, which could weaken the pavers. Hydraulic cylinders lift the mold, leaving the pavers on the press board. The press board slides out and the mold once again gets filled in and makes another 50 paver stones. It only takes about 10 seconds to mold, compact, and release a batch of pavers. The press boards filled with pavers slide into a rack. A hydraulic chain hoist lifts each board into a large holding rack. There, a special moving wagon called a finger wagon picks up all the boards from the rack in just one move. The electrical wagon moves along a rail to a curing kiln, where it's almost 38 degrees Celsius. The pavers actually generate the heat due to a chemical reaction from the combination of cement and water. About 12 hours later, the finger wagon carts the pavers out of the kiln. They're now 70% cured as a result of the chemical process that binds the cement, sand, and gravel, causing the pavers to harden. The rest of the curing will happen over the next 28 days. The pavers are now sturdy enough to handle, so 4 steel arms with rubber pads move in and straighten the stones on the board. These alignment arms are hydraulically driven. They arrange the concrete pavers so they interlock snugly. Now, hydraulic clamp arms lift the pavers off the board and begin to pile them up. They're making a cube of stone. This stacking machine is called a cuber. It packs 9 or 10 layers of pavers on top of one another to make this cube. The cube is actually called a bundle. It will be strapped and shipped out to the job site. These concrete pavers will be on the road soon, in more ways than one.
Steelmaking usually begins with a pile of scrap metal. Using this 10-ton electromagnet, scrap iron composed of crushed car bodies, electric appliances, cans, and other steel scraps are gathered up. This powerful magnet is able to lift 5 tons of metal. About 83% of this scrap will be transformed into bars of steel. This metal is then dumped into a basket, which, by itself, weighs 32 tons. The basket can hold up to 60 tons of metal, and now they're going to melt the metal. This furnace reaches a temperature of 1650 degrees centigrade, hot enough to liquefy the metal. It is heated by 3 electrodes and by 4 natural gas burners. The contents of the basket are dumped into the furnace. Here, the pieces of metal come into contact with liquefied steel, which always remains at the bottom of the furnace. There's a reaction, and an aeration system draws out the smoke that's produced. At this high heat, the 60 tons of metal will melt in about 60 minutes. Then the cover is placed on the furnace. This liquid is composed of impurities, which rise to the surface when the metal becomes molten. At this stage, a workman draws a sample of steel to determine its chemical makeup. And now they make use of a supersonic oxygen lance. This lance blows oxygen into the molten steel, which reduces its carbon content, homogenizes the mix, and then speeds up the melting process. A ladle is positioned beneath the furnace. The molten steel will be transferred from the furnace into this ladle. The molten steel easily pours into the ladle. The ladle weighs 55 tons and holds 115 tons of molten steel. An overhead crane capable of lifting 180 tons carries the ladle filled with steel. Additives are introduced in order to obtain the correct steel tone. Here, the electrodes are taken out of the furnace ladle. A workman now opens the pouring nozzles of the distributor, equipped with 4 pouring holes. The molten steel runs into molds. It very quickly cools and begins to harden. Steel billets are produced in lengths varying between 4.5 meters and 10.6 meters. The billets are then cut to the desired length with a natural gas torch. A pouring identification number is marked on them with a wax crayon. The difference between a steel billet and the nearly finished flattened product is clear. Flattening of the billets remains to be done. Before flattening begins, billets are placed in the furnace to be reheated for 2 hours at 1095 degrees centigrade. Water jets cool the billet ejector. The billets are placed on the flattener, where powerful rollers compress them. This operation gives the billets the required shape and size. Water-cooled rollers crush the billets. Some billets go from a thickness of 12 centimeters down to 14 millimeters, while others reduce from 15 centimeters down to 19 millimeters. At the end of production, bars move along at a speed reaching 35 kilometers per hour. Once reaching their required dimensions, the bars must be cooled. This cooling bed allows the steel bars to cool uniformly. A total of some 400,000 tons of steel bars are made at this plant each year.
Ceramic tiles are a popular choice for flooring, kitchen backsplashes, and bathroom walls. They can withstand humidity and won't absorb liquids or odors. They're also fireproof, fade-resistant, and stain-resistant. And no matter how much you walk on them, ceramic tiles never wear out. This factory specializes in wall tiles. Floor tiles are made using the same process, but a different composition of ingredients. The starting ingredient here is talc, a soft, powdery mineral. They blend it with 4 different powdered chemicals, the names of which are a company secret. The ingredients go into a mixer, where they're hydrated until they're 6% water to 94% powder. The mixer runs for precisely 12 minutes. Any longer would heat the mixture and dry it out. The mixture is now slightly damp and quite lumpy. A conveyor belt transports it to a grinder that mills it to a fine texture. This mixture is now ready to be formed into various models of tiles. The factory uses fully automated machinery to produce its 10.8 centimeter square tiles, a standard wall tile size. A moving tray first deposits a batch of mixture into a mold. The mold's cavity is in the shape of 6 upside-down tiles. A press descends, applying both heat and pressure. This compacts the mixture into the cavity, solidifying the shape. As the press rises, the mold automatically pops out the tiles. They roll off the machine onto a conveyor belt. The belt now flips the tiles right side up without breaking them, which is quite a feat considering that these yet-to-be-baked tiles aren't fully hardened. The equipment is precision adjusted to handle the tiles gently at all production phases. A revolving brush now sweeps the tiles clean. Their surface must be free of dust and other contaminants for paint to adhere properly. The factory uses a water-based paint that's specifically designed for ceramics. It continually circulates in the vat, keeping the color well blended. The painting process resembles an automatic car wash. The tiles travel through 4 spray zones, each of which applies a thin coat of paint. Then they pass under powerful heating elements, which dry the paint in mere seconds. All that's left is to bake the tiles, which we'll see shortly. The factory uses the same ceramic mixture to produce these square border tiles. They look just like the other wall tiles, except that 2 of the sides are rounded. When you install a row of these border tiles above the regular tiles, the rounded edges produce a clean, finished look. While the factory uses the same painting process for border tiles, the molding process, as you just saw, is somewhat different. Rather than being fully automated, it requires some manual labor due to the tile's complex shape. That's why border tiles are often more expensive than regular tiles. When the tiles come out of the dryer, workers stack them on wooden racks. They load the racks onto mobile carts, then roll the carts into a gas-powered oven called a kiln. This factory's kiln is 58 meters in length, longer than an Olympic-sized swimming pool, and large enough to bake some 50,000 wall tiles in one shot. The firing, as it's called, takes 14 hours. Any sudden changes in temperature could produce thermal shock and crack the tiles, so it starts out at 200 degrees Celsius, climbing gradually to a peak of 1,075 degrees, then descending slowly back to the starting temperature. After a cooling period that lasts roughly an hour, the tiles come out. They're now fully hardened and ready to have their back to the wall. Laminate is a thin decorative surface layer that's usually glued onto a particle board base to create a countertop. Laminate is by far the most affordable countertop material on the market. It comes in endless choices of colors and patterns, from solids to simulated wood or granite. They also use laminate for kitchen cabinets, furniture, and laboratory surfaces. And they manufacture fast food restaurant seating, among other things, out of a thicker, solid form of the material called compact laminate. The back of a laminate sheet is made of a type of craft paper that can be saturated without becoming soggy and tearing. A treater drenches it with resin containing phenol, a compound derived from benzene. The resin doesn't merely coat the paper, it absorbs right through. The paper then enters a drying oven. The hot air cures the resin in a matter of seconds. Now they can wind the paper into a roll. The top of the laminate is called the decorative layer. It's a sheet of paper in either a printed design or a solid color. Solid color papers go through a treater that impregnates them with a more durable melamine resin. Durability is essential because the decorative layer must withstand wear and tear. Two big rollers wring out the excess resin, then the saturated paper goes through a drying oven. With the resin now cured, a cutter slices the paper into sheets. Before resin treatment, the paper was flexible and easy to tear. Now it's stiff and brittle. Bend it, and it snaps like a potato chip. While the rolls of saturated craft paper get cut into sheets, workers prepare the other style of decorative layers, those with printed designs such as simulated wood grains and granite. The treatment process for these papers is quite different than that for the solid color papers. Workers start by cutting them into sheets the same length as the craft paper sheets. These papers don't go into a treater to be saturated with resin. Instead, workers stack them, placing an overlay on each one. An overlay is a transparent sheet of paper that's saturated with melamine resin. Workers stack the solid color sheets in the same pile, but those don't need overlays because they've already been resin saturated. Now the stack goes to the press room. There, workers put saturated craft paper under each decorative layer. On top of each decorative layer, they lay a textured plate. This will prevent the finished laminates from sticking together. Everything now goes into a press. The intense heat and pressure compress the layers. The overlays bond to the printed papers, and the saturated craft paper bonds to each decorative layer, creating laminate sheets. The textured plates between each set, meanwhile, imprint their pattern onto the heat-softened resin, texturing the laminate surface. The laminates come out of the press fully cured. On the finishing line, machines trim off any excess paper on the edges and sand the back of the sheets. This helps the laminate adhere better when glued to particle board or another type of substrate. To produce compact laminates, workers compile a thick stack of black saturated craft papers and sandwich it between two decorative layers. The press melts and bonds all the sheets into a solid unit. Alternating colors produces a striped edge. Compact laminates are so thick they're entirely self-supporting, so unlike laminate sheets, they don't need to be applied to a substrate.
Drill bits are attachments you fasten to drilling tools. A taper point drill narrows to a point so the threads of the screw grab the wood. A countersink makes the top of the hole the same diameter as the screw head so that the head lies flush or below the surface. A plug cutter removes a round piece of wood with which you plug the hole afterwards to hide the sunken screw. Countersinks and plug cutters start out as steel bars. To make a countersink, this computer-guided tooling machine uses what's called a center drill to pierce a starting hole, then switches to its main drill, which bores right through. Next, it uses what's called a rough turning tool to shape the countersink's angled nose, then its body. The machine now switches to a milling cutter. This tool shapes the countersink's 4 blades. A cross-drilling tool bores a hole for the 2 screws that'll hold the countersink to the drill. A tap cuts threads into the hole. Next, a tool called a dovetail cutter sharpens the blades. Then finally, a cut-off blade removes the tool. The same machine makes plug cutters. Its center drill makes a starting hole, but this time, the main drill doesn't bore right through. It stops at the depth that the plug cutter is designed to cut. Just as before, the rough turning tool shapes the body, and the milling cutter sculpts the 4 blades. Some plug cutters on the market have fewer blades. This company makes 4, so the cutter will clear the wood chips more efficiently when it tunnels into the wood. After the dovetail cutter sharpens the blades, a tool called a boring bar refines the hole in the center, making it the proper size. Another turning tool now forms the shank, the stem of the plug cutter that you insert in the power tool. Then the cut-off blade slices the tool off. Now for some manual touch-ups. First, they grind the plug cutter against an abrasive wheel to remove excess metal from the cut-off. Then they do what's called side chipping, grinding the sides of each blade to a particular shape that'll clear the wood chips. Here's how the plug cutter looks before and after grinding off the excess, and before and after side chipping. And now for making the drills to which the countersinks attach. It all starts with a tapered piece of steel, because this will become a taper point drill. Straight drills begin with a straight piece. A mechanical arm inserts this drill blank, as it's called, into a computer-guided grinder. The machine has 2 wheels made of boron nitride granules, a natural material that's tough and abrasive. The first wheel shapes the smooth blank into lengthwise spirals called flutes. A second wheel then grinds sharp cutting edges on the flutes and shapes the tip of the drill to a point. Back to the countersinks now. The steel is still relatively malleable, so a worker runs each one through a stamping machine that imprints the size of the tool and the company name. Whereas the drills are made of a different type of steel that's already hard enough, the countersinks and plug cutters must undergo a heat treating process to harden, about 20 minutes in a fiery oven, along with a secret recipe of chemicals. The intense heat, 955 degrees Celsius, transforms those chemicals into gases which then permeate and harden the steel. After cooling in warm water and oil for about 15 minutes, workers submerge the tools in an industrial-strength cleaning solution that removes all the oil grit. Then a bath in acid to remove soot from the oven. Then finally, 20 minutes in a blackening solution, the ingredients of which are again a closely guarded company secret. This last step is purely cosmetic. So, how do the 3 drill bits we've seen all work together? First, you use the plug cutter to make the plug. Then you pop out the plug with a screwdriver. Next, mounting the countersink, that black tool, onto the taper point drill, you drill a hole for the screw. Then you drive the screw into the hole, sinking it below the surface. Then you cap the hole with the plug. These tools come in an extensive range of sizes and grades for both amateur and professional woodworkers, and for industrial machines. It's pink and fluffy, and it keeps us warm. Fiberglass insulation is a blanket solution for heat loss from our buildings. It has a woolly texture, but it is, as the name suggests, made of very fine threads of glass. That's why it's sometimes referred to as glass wool. It's pink, but the premise is green because fiberglass insulation is made from at least 35% recycled glass. The recipe also includes what's called the batch, a lot of sand and smaller portions of soda ash, limestone, and other minerals. The glass, called cullet, used to be bottles and windows. This will be its second recycling. The cullet and batch ingredients spill onto a conveyor belt system, which transports it all to an electric furnace. The conveyor moves back and forth to evenly distribute the cullet and batch ingredients. They seep down and melt into a previous mix, which is now a pool of glass at the bottom of the furnace. The glass liquid now flows out of the furnace and into sloped channels. Inside these channels, the temperature is kept red hot by natural gas burners. This keeps the glass mix in a liquid form, as it oozes out of holes in the bottoms of the channels. The melted glass falls about a meter into a spinning bowl. It's called a fiberizer. The spinning action flings the glass through thousands of holes in the bowl, creating thousands of feathery glass fibers. Gas and compressed air pull the fibers, stretching them thinner. The process is a lot like making cotton candy, and the spun glass even has a similar texture. But the fibers will soon become even more like cotton candy. Nozzles spray them with a polymer glue tinted pink. The now pink and sticky fibers drop into a hole in the ground and amass. Then a conveyor belt takes the mounds of sticky glass to an oven. Steel plates compress the pack as it enters the oven that's heated to 260 degrees Celsius. Hot air blows through it, setting the glue. As the pack exits the oven, circular saws cut through it, making 38 to 60 centimeter wide strips that are called lanes. The lanes pass by a series of poles that push them apart. An inkjet brands each lane with a number that conveys the R value. R stands for resistance to heat flow. It's a measure of how well the insulation will stop heat from going through the roof, and your energy bill along with it. A chopper with big steel teeth now cuts the lanes, making chunks that could easily be installed in an attic or wall. After chopping, the conveyor belt accelerates, transporting the fiberglass bats to the next station. A few at a time, the bats plunge down a chute to a mechanical arm which slides the bats into a compression chamber. There, a hydraulic ram squishes the bats down, reducing their bulk 5 to 10 times. This compaction will make them easier to transport. Now, another ram comes from the side and pushes a stack of compressed bats forward into a spout. The spout is a hollow bat-shaped frame. A worker pulls a plastic bag over it. Then the ram pushes the fiberglass insulation bat into the plastic bag. And the process begins again. A conveyor belt transports the bat-filled bags to a machine that heat seals them. And that's literally a wrap for this production.
There was a time when exposing your hardwood floors meant you just couldn't afford wall-to-wall carpeting. Not anymore. Hardwood floors are definitely in. And today there are so many wood and stain color choices, hardwood floors can suit any decor. The types of wood commonly used for flooring include red oak, beech, maple, white oak, walnut, birch, and ash. As soon as the wood arrives from the sawmill, workers at the floor factory stack it on racks, then pile the racks floor to ceiling in a dryer that's the size of a large barn. There, large fans circulate hot air around the racks. The wood's moisture content is between 40 and 60% depending on the season. When that drops to about 7%, the wood is ready to come out. This drying process takes anywhere from 10 days to a month. The length of time varies because some species dry out much slower than others. The wood is in random lengths and widths, so the first step after drying is to cut it to standard sizes. On the way to the ripsaw, the planks pass under an optical device called an optimizer. In mere seconds, it reads the dimensions of each plank and sends that information to a computer. The computer calculates the greatest number of standard-sized pieces that can be cut from the plank, then guides the ripsaw to cut accordingly. This maximizes the yield and limits waste. Flooring is made from medium quality rather than top quality lumber to keep prices competitive. As the pieces exit the saw, workers manually cut out any large knots or other defects, weak points at which a piece could potentially snap and jam up the equipment. The pieces now travel to a machine called the molder. Its revolving steel knives spin at a rate of 6,000 rotations per minute, carving a tongue down one side of each piece and a groove down the other. Workers do frequent spot checks to make sure the tongues and grooves fit together snugly. The next machine carves grooves on what will be the underside of the pieces. This is for air circulation and stability. Then, an embossed wheel imprints the words, "Made in Canada." Using cross-cut saws, workers remove any faults in the wood and divide pieces that have noticeable color variations. This is the first step towards sorting the wood by grade. Now a machine called an end matcher carves a tongue and groove on the two ends. Here's the view from inside the machine. Workers check once again for faults. Then, assessing quality and color, sort each piece by grade. This will be pre-finished flooring, so the pieces now run through a sander to prepare them to receive 8 coats of varnish. For certain finishes, the first coat contains wood stain. All subsequent coats are colorless. Between each application, ultraviolet lamps dry the varnish in just a few seconds. As the flooring exits the last drying oven, it's ready for packaging. Unfinished hardwood flooring has to be sanded, stained, and varnished after it's installed. Pre-finished flooring eliminates that extra work, sparing you the dust, the drying time, and the smell.
There are hundreds of varieties of nails being made, and they're made of very durable carbon steel, all starting from steel wire. Rolled up on a drum, this steel wire weighs in at 2,045 kilos. The wire's diameter is 6 millimeters, and that's too large, so they'll have to reduce its size. Using many drums, they're going to pull the wire successively to gradually thin it. Then they'll roll it up again. When full, this roll will contain 23,500 meters of wire weighing 1,136 kilos. The wire now has a diameter of 2.84 millimeters, so it will have to be reduced by half. Now they're going to cut the wire into little rods. The cut rods are gathered up with this electromagnet and dumped into a machine that will process them. Here the rods are made into nails. The metal rods move along slowly and a blade forms the nail points. These blades are changed every 600 hours. This machine forms nail heads by flattening them with great pressure on the rod ends. Nail heads are formed at a rate of 1,400 per minute. The manufacturing of nails is now finished. They fall into a chute, then into this collecting bin. Nails are sold by the pound or embedded in plastic rolls, as we see here. This machine inserts 167 nails into each roll. The plastic strip has teeth, and the nails hook into these. They handle the rolls with gloves, since the coating applied to the nails is not yet dry. This machine produces 5 rolls a minute for a total of 835 nails. Making spiral nails requires an extra processing step. This machine puts the spiral into the nails with these cylinders and welds them. It makes 1,200 nails a minute. Then the nails are put together into strips for use in pneumatic nailing guns. Each strip contains 30 spiral nails. To help them stay in place, the nails are coated with a resin that dries in 4 minutes. This is the nailing device that uses nails on a strip. It sets the nails in one strike with the user's trigger finger. Now, we move on to the fabrication of staples. The staple press binds 80 iron wires which have been well lined up. The 80 small wires are placed side by side. The wires are glued together. Then the wires come out well adhered to one another. The staple strips are fed into this machine. It cuts the staples to the desired length and folds them in one stroke of this press, which applies 40 tons of pressure. Staples are formed on this gauge, and the staple strips are then ready for packaging. Every day, they produce a total of some 25 million nails here, which require the processing of 10,000 tons of metal annually.
Asphalt is a black liquid substance that's a byproduct of processing crude petroleum. Asphalt is a key component of waterproofing and insulation materials and roofing shingles. But its best-known use is for paving roads. Asphalt cement is a byproduct of crude oil, the key ingredient they mix with crushed rocks and other minerals to make paving asphalt. So production begins at the paving plant's quarry, where some 15 meters below ground, workers driving heavy machinery collect boulders of granite that have been blasted off the rock walls.
Trucks transport the rocks to the paving plant, which is right on the quarry site. They dump their cargo into the primary crusher, a machine whose steel jaws crush these big rocks into pieces smaller than 20 centimeters. It takes mammoth force to crush solid rock. The flywheels that amplify the motor's energy weigh more than 6 metric tons. The primary crusher empties onto a mobile conveyor belt, which transports the crushed rocks to an outdoor storage area. When it's time to make the asphalt, the rocks travel via conveyor belt from the storage area to a screening building to be classified by size. There, the rocks tumble downward over a series of inclined screens whose largest holes are 10 centimeters big. What's too large to drop through goes to a secondary crusher that reduces the rocks to 10 centimeters or smaller, then sends them to a third or tertiary crusher that further reduces them to 2 centimeters or smaller. What's small enough to pass through the screens bypasses the secondary crusher and goes directly to the tertiary crusher. After this last crushing stage, the largest stones are 2 centimeters in size. Everything smaller than 5 millimeters goes in one pile. That includes stone dust created by the crushing process. Stones 10 to 14 millimeters go into another pile. Stones 5 to 10 millimeters into another. Trucks transfer material from each pile to separate compartments called feed bins. Exactly what goes into the paving asphalt depends on what's being paved, but generally, these are the 4 ingredients. Sand, stone dust, 5 to 10 millimeter stone, and 10 to 14 millimeter stone. The ingredient proportions vary according to what the paving asphalt will be used for. Stones, along with sand and stone dust as fillers, usually make up about 95% of the mix. The remainder, added later, will be liquid asphalt cement. Each bin releases a specific amount of material onto a conveyor belt running under it. The belts lead to a main collecting belt that dumps the ingredients combined onto yet another belt that leads to a dryer. The drying process, which takes about a minute, removes all traces of humidity. This will enable the materials to bond better with the asphalt cement. Screening equipment then re-separates the dried ingredients, making it possible to precisely weigh out the required amount of each one. Everything then goes into a mixer. As this demonstration shows, the mixer blends everything thoroughly. Then it's time to pump in hot asphalt cement. Oil refineries make asphalt cement from what's left over after they've processed crude oil. The paving mix contains about 5% asphalt cement. This is what happens inside the mixer. The hot asphalt cement binds the ingredients in about 30 seconds. The result is ready-to-lay paving asphalt. The mixer empties directly into trucks destined for the paving site. There, a paving machine will spread the hot asphalt on the road bed. Then, a compactor roller will pack it down. The asphalt cools and hardens in about 1 hour, depending on the weather.
Years ago, people went to great lengths to make rope. They stretched yarn 200 to 300 meters, sometimes down alleys, and secured it on hooks. Then they turned wheels to rotate the hooks, twisting the yarn into rope. This technique was called a rope walk. Luckily today, we have machines to do all the legwork. These ropes are made from thousands of nylon fibers that are finer than human hair, but stronger. To make rope, yarns wind around aluminum cylinders, pulled by a turning spool down the line. Then, 3 at a time, the yarns roll over another spool that applies a protective coating of urethane. Then they funnel through a distribution plate that holds them evenly apart. This ensures they're at an even tension as a rocking spool twists them into one larger yarn. This machine is called the whirlwind. It twists the yarn and then winds it onto a take-up spool inside. A little arm moves back and forth, guiding the yarn so it winds evenly onto the spool. This is core yarn, and it'll be used to make other rope. Now, dozens of spools of nylon fiber unwind at the same time to make jackets to protect the core yarns. The fibers travel several meters over a network of rollers that act as guides and control tension on each individual fiber. They pass through distribution plates, as turning bobbins below twist the fibers into yarn. The platform moves up and down to evenly wind the yarn onto the bobbin. They place 48 of these bobbins on the maypole machine, so called because the braiding action resembles a dance around a traditional maypole. The bobbins spin and zigzag around each other as the machine pulls core yarn up through the center. Here you can see the rope being braided around the core yarn as it's pulled up through a die. This is the braiding action in slow motion. It produces a mountain climbing rope, strong yet stretchy because of the twist in the core of the rope. The rope winds onto the wheel as it pulls it upwards. Then it spills into a basket. A worker pulls out a sample rope to check its flexibility and strength. He bends it to make sure it'll knot easily. Now another maypole braider weaves a synthetic rope that's stronger than steel, yet lightweight and flexible. That's because the strands at the core are braided with a material called ultra-high molecular weight polyethylene. It's a high-performance thermoplastic. This rope will be used for advanced yachting. A pulley draws this high-tech rope through some metal pipes filled with steam. This shrinks the polyester jacket around the powerful core for a tight fit. These dancing bobbins do some fancy moves to produce different weaves around core ropes. They dip around and between each other in a choreographed sequence. But there are no worries about production hitting a snarl. If a yarn breaks, the machine simply shuts down. It takes 8 to 10 hours to make a bit more than 900 meters of this large utility rope. Now for the strength test. They loop a sample piece of rope around steel posts. This one is a nylon double braid, the type used for dock lines on boats. Hydraulic pressure pulls the rope upwards, while a computerized gauge measures the tension and detects the breaking point. Over 9,000 kilograms. That's the weight of a killer whale. Needless to say, this twine is just fine. Now for another test. They insert a steel probe, known as a fid, into some industrial rope, then place the pointed end into a hole. An electric motor forces the fid through, while a gauge measures the force it takes for it to completely penetrate the rope. It took 4.5 kilograms of pressure to push the probe through the rope, which means this rope is firm yet flexible. So now you really know the ropes about rope.
Used tires are a real source of pollution. This pile represents about 100,000 of them. At any rate, these tires will have a second life. They'll be recycled to make rubber mats. Each day in this factory, they recycle 15,000 tires into mats. Tires have to be reduced to little granules, but first, this conveyor feeds the tires into the washer. Tires are washed with a water-based biodegradable preparation. Then they're sent to the shredder. The shredder has 2 rows of large teeth. These grind up the tires into pieces. This shredder is able to cut up almost 1,000 tires an hour. They come out as fairly good-sized pieces of tires, which are then shredded a second time. Metal is magnetically separated from the rubber, and the metal pieces are recycled at another factory. Other components of the tires, such as fiberglass and nylon, also have to be separated. They use a sifter to get out unwanted rubbish. Recuperated rubber particles purged of foreign materials measure about 2.5 millimeters. Some 16 tons of tire particles are piled up in this recycling depot. But the particles are still too large to be used. They're sent to a secondary shredder's supply tank where they'll be reduced even further. This tractor feeds the secondary shredder. Grinding action produces a kind of rubber powder. The powder is spread out on these enormous molds. This mold has a length of 7 meters and a width of 1.2 meters. Thickness varies according to the product being made. The molds filled with rubber powder are stored in this loading magazine of the press. Once full, the molds are sent to the rubber mat press. Here's the mat press. The powder has to be cooked at a very high temperature for about 30 minutes. Cooking time depends on the product being made. The cooked mat goes through the unmolding unit before being sent off to cool. The rubber mats are still extremely hot. They're cooled with jets of water for a period of several minutes. The cooled mats can now be sent to the next department. This conveyor in the cutting center positions the mat before it's cut. The mat is vibrated to eliminate any surplus water. Each rubber mat is now cut up into 3 pieces. The cut mats are then stacked into a pile and stored before being shipped. The company also makes mud guards. These are fabricated the same way as the preceding mats. After having been cooled in water, but while they're still warm, they remove the surplus rubber. This operation is called notching. Hard rubber rings are also produced at this facility with the same fabrication methods and, as always, from old used tires. Over a 12-hour period, this facility makes no less than 12,000 rubber mats from old recycled tires. This translates into good news for our environment.
There was a time when if you wanted to build something out of wood, you had to pick up an axe and go chop down a tree. Thankfully, for city dwellers, all it takes today is a trip to your local renovation center to buy 2x4s, 2x10s, you name it. They start with logs cut from spruce or fir trees. Turning them into construction wood isn't that complicated. First, they soak the logs for about 20 minutes. This removes the mud and softens the bark to make it easier to remove. Next, the logs go through the debarker, a machine with a rotor that shaves off the bark. The rotor has 6 sharp blades that take just 10 seconds to shave a log bare. In the filing room, they regularly sharpen and inspect the saw blades they'll use to cut the shaved logs. straightening them back into shape when necessary. In this sawmill, there are two production lines. The wider logs go through this saw. The worker at the controls uses a laser to help him position and reposition each log as he runs it through the saw several times to cut it into as many 4 by 10-inch pieces as possible. An average log usually yields about 7 or 8 pieces. The narrower logs go through a different saw. This saw first cuts a board off each side, then sends what's left of the log onto another saw. The 4 by 10s on the first production line go for a second cut called the resaw. They're cut in half into 2 by 10s. The logs on the second production line end up here in what's called the Canterbull machine. It has 8 adjustable circular saws that can cut the log into various sizes of wood, anywhere from 2 by 3s to 2 by 8s, depending on the log's diameter. Both production lines feed to machines that smooth the edges and trim off any defects that can affect the strength or resistance of the wood. Then an automated sorter drops the wood into bins according to their size. Each bin then feeds the stacking machine. From here, they'll put the wood into a kiln to be dried to about 15% humidity. Then they'll grade the pieces and ship them to a lumber yard or renovation store. We open and close them several times a day, day in and day out, and seldom give them a second thought. But imagine your home without doors. For one thing, you'd have absolutely no privacy. And what would you slam when you get angry? The first factory makes the doors plywood facing. They start by loading logs into steaming basins for 3 days. This de-ices them in the winter and softens the wood fiber. Inside the factory, the steamed logs line up for the debarker, a machine that removes the bark. The operator projects concentric circles and uses a laser to carefully center the log on the debarker. Positioning is crucial for 2 reasons: so that as little wood as possible comes off with the bark, and to ensure the debarked log ends up perfectly cylindrical. That maximizes the amount of wood veneer a log will yield. The next step is called rotary cutting. As the log spins, a lathe skims off a sheet of wood veneer just 0.6 of a millimeter thick. The average log yields 134 linear meters of veneer. Next, they unroll the veneer and cut it into sheets. Then they stack the sheets by identical grain patterns. Using a laser to position the blade, they cut through the stack to take out visual defects. Then they glue the pieces together. To make veneer sheets for the front of the plywood door facing the side that will show, they line up the wood's grain and other features in mirror image. For the back, the side that won't show, they assemble the defective parts they cut out earlier. They use 3 veneer sheets to make up the plywood door facing. They apply glue to both sides of one sheet, then sandwich it between 2 other sheets. They feed the 3 sheets through a hot press at more than 100 degrees Celsius. In a minute and a half, the glue cures, and those 3 sheets of veneer become a 3-ply panel of plywood. Then they sand the panel. Plywood door facings can be made from more than 15 different species of wood, from birch and oak to maple and mahogany. At the second factory, they make the core of the door. They glue together strips of wood to form the middle, then frame them with pieces of white pine. A press pushes the core pieces together, then activates the glue not by heat as most presses do, but by microwaves. Next, they sand and calibrate the core. After the glue machine coats the core, they stick a plywood door facing on each side. They stack a few doors at a time into a cold press for a half hour until the glue dries. Then set them aside while the glue cures for another 8 hours. Next, they size the width and length to the final dimension, bevel the edges, and cut the exact height of the door. Then they inspect the door on both sides. A machine prepares the door for hinges. Then another machine cuts the hole for the knob. The finishing process takes just 70 seconds per door. One side is sanded, stained, and sealed, then sanded again and varnished. The machine then flips the door over and does the same thing to the other side.
One of the most interesting and potentially life-changing developments is the creation of a concrete canvas. It's basically a material that consists of all the elements of concrete, but it's flexible enough to be turned into any shape.
However, once it's been submerged in water and given time to set, it becomes completely solid. Now, the implications of this new technology are far-reaching because it's going to allow people to erect permanent structures, but in a fraction of the time that it would have done using traditional building techniques.
The concrete canvas begins life in waterproof plastic sheeting for easy transportation. Inside, the canvas is wrapped around an inflatable lining, which will be blown up to create a building 50 square metres in size. But first, water must be piped inside the package to start the process of dampening the cloth.
It should take about 800 to 1,000 litres.
Right, okay.
But essentially there's no measuring, you just fill the sack entirely with water.
The concrete cloth is made up of fibres which evenly absorb water until all of the cloth is saturated. The inspiration came from the plaster casts wrapped around broken bones in hospitals. Once the cloth is completely soaked, the process of hydration begins and the plastic casing can be removed. At this point, there's a window of around 5 hours for the canvas to be raised into its final position before the concrete starts to set.
The next stage is to fit the blower. The blower's on.
The only other bit of gear you need is something to drag out the cloth so it's completely unfolded before it's inflated.
I still can't imagine what it's going to look like, but I can't believe that that little blower is lifting that weight.
It's amazing, isn't it?
The speed with which this technology can be used may allow huge improvements in how the world reacts to humanitarian crises. A concrete canvas building has good thermal properties, so whatever's inside is kept either cool or warm, and it can even provide a sterile environment for surgery.
Yeah, I didn't realise there were going to be doors on it.
Has it got a door?
Yeah, look at that.
Goodness me, you thought of everything, didn't you? You can actually get in it.
And just a day later, it's ready to walk in and use. It's strong enough to stand on, endure hammer blows, and even the heat from a blowtorch.